I was gonna tell this girl that I found out standard deviation.
Okay, let's go ahead and get started. First of all, are there any questions on the homework?
Yes. The
The vectors. Okay, well today we're going to cover vectors. Any other questions? We'll get to those after.
3B.
Which one's that?
My calculator kept telling me it didn't work. Syntax error. I don't know what I'm doing wrong.
Can you give me the problem?
It's
Oh, that's
one of the
a
triangles.
phone. I thought it was a fire alarm.
I punched in sine
Well, what's the problem? I just need to know the problem.
Use a right
3B. Yeah, it's a right triangle.
two, one side for the other, and the hypotenuse is what it was.
Okay. So this one?
Yeah,
One that you have what?
that's missing.
That's missing, yes. And the hypotenuse is missing. And then that's 2, and the bottom's 4. Centimeters.
Okay.
And the bottom's 4.
This one's 4?
4 centimeters, yep.
This is the right triangle.
Yep.
Okay, and what was the problem?
Apparently I did sine. I should have done tangent.
Oh, yeah. If you did sine, well,
I mean,
even then,
you could have done it side too if you found a third
yeah, you
side.
could do it.
I had negative sine and then 4.47 over 2. And it said it equaled syntax error.
Oh, sine to the, you mean inverse sine.
Yeah.
All right, so I see what the issue is. So you found this at 4.77.
Yeah.
Okay,
4.47.
4.47. You got that with the Pythagorean theorem.
Yeah.
Okay, and then you were using the sine of this over this.
Yeah.
Which way does sine go?
The other way apparently.
Yes. So if you found the sine of something's greater than 1, you're in trouble. Because sine is between 0 and 1.
Ah.
So trying to take the inverse sine of something bigger than 1, you'll get a syntax error.
Yeah.
That
would explain
that.
that.
Will give you that.
Fair enough. So I just had them backwards? Was
Yeah.
all that, I see.
Yeah. Nope, no, not quite. Give it a try. It might be similar, but not. It won't be 30 and 60. Well, because tangent's the one half of the sine. So if I had this 4 centimeters here, then I would have 30 degrees here. Okay. All right, well, let's talk about vectors today. That's going to use the stuff we've learned about trigonometry, and it'll also be very important later on when we talk about Newton's second law. And it will be very important to just get the homework done and to learn about, it's a good thing to learn. So first of all, a vector, we mentioned this at the end of the class last time, it's just a physical quantity, any physical quantity that has a size and a direction. That's my definition. That'll be an operational definition of vector here. See, with a size and a direction. As such, having a size and a direction, a good graphical way to represent a vector is just with an arrow. Arrow has a direction where it's pointing and a size, how long it is. Okay? Sometimes we'll also call this the magnitude of the vector. Okay. So let's take an arbitrary vector A. Represent it with an arrow. When I write out a vector, something that has a vector, to keep it straight from other things in algebra that don't have arrows, I'm always going to make sure I put a little arrow sign over this. I think probably one of the easiest mistakes to make is to lose track of what's a vector and what's not, okay? And so make sure you keep it straight by putting an arrow over all vectors. Make sense? All right, so let's say I have a vector A. It becomes very convenient to write this, to represent these things using what a coordinate system. You know, A points in this direction, has some size. What I really want to do is be able to write it down so I know how much it goes in some direction, how much it goes in another direction. So I got to define what we're talking about when we talk about directions. And that means introducing what's a coordinate system of some sort. So in this class, we're mostly going to deal with a Cartesian system. What that means, basically an XY coordinate system. Okay, like that. Then, for instance, I know the vector goes this far in the A direction and this far in the Y direction. Makes sense? So this distance here is how much it goes in the in the X direction. I'm going to represent that as A sub X. This distance here is how far it goes in the Y direction. I'm going to represent that as A sub Y. That how far it goes. And A sub X and A sub Y are what are known as the components of the vector, the X and Y components of the vector. Components of the vector. If I'm talking about the size of the vector, I can say that the total length of the vector, length or size or magnitude of the vector, we'll represent it, we'll write it as absolute value of A, or modulus of A, this is sometimes called, magnitude of A, any of those things. So graphically, this thing is equal to the modulus of A, that length here, or magnitude of A. Does that make sense? So if I have this thing being the magnitude of A, this thing being the components of A, if I knew an angle here and a magnitude, I could get these components because it looks like I have a right triangle. And that is indeed the case. We're going to be using our trigonometry to get those components. So for instance, if this angle is the angle of the vector with respect to the x-axis, however we've defined the x-axis, then A sub x can be written in terms of the magnitude of A and some trigonometric function. Can you guys figure out what that is?
Can you say that again?
So I can write this length, the x component of A, in terms of this magnitude of A, or the length of this vector, and something from trigonometry involving this angle.
So it's going to be adjacent or the...
Yeah. So the cosine of that angle, the adjacent side, this is a right triangle here. That's the adjacent side, as I have it written, that's an x component, right, over the hypotenuse. Like that. You guys follow? The
The adjacent side is the longer side that touches the 90.
No, the adjacent side, this is the angle, the adjacent side of this angle is the non-hypotenuse side that touches that angle. Okay?
Okay.
So that would be.
The
this
hypotenuse side is the top side.
side. Yep. Hypotenuse is the longest side of the triangle, of the right triangle. That makes sense, where I got this? So what would a sub x be?
Cosine of theta divided by that thing.
Well, if I multiply both sides by magnitude
Oh,
of
you
a.
multiplied everything.
These cancel and I get a sub x is just magnitude of a cosine of theta right here. So take about a minute, figure out what a sub y is in terms of magnitude of a and that angle. You lost? You got it? What do you get?
It should be a sub y equals the
Magnitude of A.
sine of the angle.
Good. So, a sine, the angle, let's see where that comes from. So sine of that angle is going to be the opposite over the hypotenuse, this distance is y, over magnitude of a. So if I multiply both sides by the magnitude of the vector, I'd get the magnitude of a, sine of the angle is a sub y. Okay? Good. Let me give you a problem. This one will look slightly different. You have to do a little geometry work to get it. All right. Let's introduce a map. And maps, you know, you have the north, east, and compass rose, southwest. And let's say a crow flies 500 miles at an angle of 30 degrees east of north. How far did the crow go in the north direction? Far north. Crow go. So see if you can get that. You can work with the person next to you if you want. Okay?
The angle you're saying is from north.
30 degrees east of north. So
Yeah. Yeah, that's what I have.
you get it.
500 miles to the hypotenuse.
Yes,
500. And then how far east is it? So we're gonna get to the bottom. 30 or something? Which one's closer? Yeah, okay, yeah.
That's it. No, you did it right. You did it right.
Sine 3,500.
What? So,
No, my calculator's all out of whack. I don't know what's wrong.
Oh, yeah.
Mine is a little more.
Chris, you had the right idea.
yeah. Oh, you were maybe in the Thank you.
Did you get 4? Yes.
You might have been in the Navy position. I don't know. I think that's my idea.
Okay. That's just.
It's a tricky problem.
Did you put that angle on?
So, not in the end.
Okay, raise your hand if you have an answer. All right, looks like pretty much everyone. So let's take a look at some of these answers. So, what answers do we have?
433.
433 miles north. Any others?
250?
250, all right. Okay, any others? All right, well, let's go ahead and take a look at how to do this. First of all, this is a magnitude and a direction, that distance that Crow traveled. I'm going to call this vector R. Just kind of label it that way. And the magnitude of R is 500 miles. Okay. If I read this angle of 30 degrees east of north, that means that this angle is the angle in question. That's the 30 degrees. Okay? And so that would make, since there's a 90-degree angle between north and east, that would make this angle 60 degrees. Now I'm going to introduce my usual coordinate system. X, Y, so Y points in the north direction, X points in the east direction. I see how far north did the Crow go. What I'm really interested in is the Y component, R sub Y, of that position vector. Make sense?
So, like, how do you know that that 30 degrees is not where the 60 is? Like, can you?
Because east is in this direction, 30 degrees east of north means I was going north, and then I went by 30 degrees down, tilted toward the east.
Okay.
So that is the key point, or the key place to make a mistake, probably. All right. And so if I want to get the R sub Y, I would take the magnitude of R, which is the 500 miles, times the sine of that 60 degrees, right?
Mm-hmm. Sine?
Couldn't you do
Cosine.
cosine of the 30 degrees as well?
Sine of 60 or cosine 30.
Yes, you could.
Oh, that's what we got.
Yes, you
An
could.
accident.
So basically, you want this length here, that's the same as this length, and that's also the cosine of 30 degrees. So, works out either way. And so this would give you that 433 miles, because that sine of 60 is square root of 3 over 2. Okay? Does that make sense?
It works. Yeah.
Good. Good. All right, let's do some more vector stuff. A lot of times, we want to add up multiple vectors. So let's say I have two vectors, and I'm not going to worry about their units or what they actually are for a little bit. Say I have two vectors, but they have the same unit that can be added together. A, and the second vector B. Maybe I'll do one just a little bit less flat. B, I'm trying to write A a little more vertical. Okay, A. Okay, let's say I have two vectors A and B, and I want to add these two things together. The way that we add vectors is we take the tail of one and place it on the head of the other. And then the resultant vector goes from the tail of one to the head of the second. So let me do this. So I'm going to say A plus B vector is going to be graphically represented as A going upwards like this, and then B with the tail of it placed on the head of A, and then this thing here from the tail of the first to the head of the second is A plus B. Okay? So graphically, this is how you add vectors. You just kind of imagine moving this over to here, and then draw some of the vectors will be from the tail of the first to the head of the second. Does that make sense? Okay. Clearly, B plus A is going to be a little bit. It'll look slightly different how I construct it, right? Because in this case, B would be the bottom one. B would be the first one, and I place A in the head of that. So this vector here is this thing here, A, B plus A, would also actually be this thing as well. That's because A plus B is kind of those things, and B plus A kind of this thing. They form the two sides of a parallelogram, the four sides of a parallelogram, I should say. And the sum of the vectors either way is the diagonal of that parallelogram. So it's going to be the same thing. So that means that A plus B is going to be equal to B plus A. So the order you add vectors doesn't matter. And that's an important thing to know. How we add vectors gives us a way that we can also kind of scale vectors. So what I mean by scaling is, let's say I look at 2A. Well, clearly 2A is the same thing, hopefully, as A plus A. That's how we would define 2A. So if I look at A plus A, if I have A like this, and I add it again to it, A, then you can clearly see that 2A is just A lengthened, because it's in the same direction. So if you multiply a vector by some constant, by vector A, by some constant, then you get a vector in the same direction, but lengthened by that constant. Then you get a vector in the same direction, but lengthened or shortened or whatever the constant is. So for instance, if this is A, then C times A is going to be a vector that is in the same direction as A, but longer by a factor of C, or shorter if C was less than 1. Does that make sense? Okay, so multiply it by a constant, keeps the same direction, just changes the magnitude.
Negative number reverse this or
Yep, if you multiply it by a negative number, you reverse it all the way. You make the direction completely negative. C is negative. So negative A is same direction but all the way reversed. So that's very good point. Okay.
you mentioned less than 1.
Yep. Less than 0 means you've actually reversed it all the way, but it's along the same line, I should say. That's a good question. All right. These things all together give us a possibility of introducing one other way of writing vectors, and we're almost done with the theory part, so we'll get a little bit less abstract in just a minute. If I introduce something called I can introduce something called a unit vector. Unit vector. These vectors have a length 1 along in some direction. Length 1. Now that's unitless 1. That's just a dimensionless 1. So if I had so if I was trying to represent a vector of with a length of 1 meter, I'd have to multiply a unit vector by a meter to get it that way. So unit vectors are special vectors that point, that have a length 1. They point along directions on the Cartesian coordinate system is what we'll use, x and y. And I'll call the vector with a length 1 pointing in the x direction x hat. It also sometimes gets called I hat. And the vector that goes in the y direction with a length 1, y hat, sometimes also j hat. I'm going to use the y hat and the x hat almost exclusively.
Why did they throw the I and the J in there? Just for extra confusion? Or?
I think so. It's a good question, actually. I don't know historically where it came from. But you know, just so you know. And then if it happens that you're in 3 dimensions, you can have a z hat coming out of the board, or it also gets called k hat. So, just so you know. Well, any vector A that's in the board, that's in the plane of the board, can be represented as the sum of 2 vectors involving those unit vectors. So let me draw an arbitrary vector A. Well, I know that the length of this A along the x direction, that's a sub x. So I could represent a vector here as a sub x, x hat. I take the unit vector x hat, scale it by the length in that direction, and then this gives me a vector here, a sub x, x hat. The length of this vector here is a sub y, or the length in the y direction is a sub y. So I could write a vector here that has the length a sub y and points in the y direction as a sub y, y hat. Adding these two vectors together gives me A. A's those two vectors added together, right? Take this A sub y hat has the tail of placed on the head of the A sub x hat. So that A is the result of those two vectors added together. So I can write A equal A sub x hat plus A sub y hat. That's one way to represent vectors in terms of unit vectors. We'll run into that a lot. Finally, let's look at what happens if we add two vectors. So let's say I have a vector B. Maybe I'll do B slightly different looking than A. Say a vector B. Okay. Then this length here in the x direction, I'm going to make sure I label my directions, would be B sub x hat. This, well, that length would be B sub x. A vector would be B sub x hat. And then this thing, this little vector going upwards, would be the amount in the y direction, y hat. So B would be B sub x hat plus B sub y hat. Okay, now let's do B plus A. So if I add A to B, where A is that vector over there, I have a A sub x hat. Let me see if I get this. A sub x hat going further over here, and A sub y hat going upwards, and then the resultant vector A plus B, B plus A, doesn't really matter since the order doesn't matter, would look like that. Notice that that resultant vector goes over a B sub x in the x direction plus another A sub x in the x direction. You see that? So B plus A would be A sub x plus B sub x hat. And it goes up a B sub y in the y direction plus another A sub y in the y direction. Okay. And then this gives us our rules for adding vectors. The x components add together and the y components add together. You would never add an x component to a y component. Never. It's the x components that add together, it's the y components that add together when we're adding vectors. All right, let's do some examples, okay? All right, so let's say I have two position vectors, R1, and let's say I have R2. And I'm going to introduce a usual XY coordinate system, and I'm going to say R1 makes an angle of 30 degrees with respect to the x-axis, and the magnitude of R1 is 10 meters. R2, I'm going to say, is along the x-axis. Magnitude of R2 is 10 meters. Okay. What I would like to see is 1A, or part 1. Write R1 and R2 in terms of Write R1 and R2 in terms of unit vectors, x and y, x hat and y hat. Terms of x hat and y hat. Write it using those unit vectors like we did over there for the a's and the b's. That'll be part 1. For part 2, add R1 plus R2 and find the resultant vector in, okay? Find, well, just add R1 and R2. Write it out in terms of unit vector. Finally, 3, what angle does R1 plus R2, that vector, make with respect to the x-axis? Make with the x-axis. All right, so those are 3 little quick problems. See if you can do these, okay?